Picking up where we left off in the last video, we are still discussing example 1 in section 8.7. We are asked to find the closed form for the Maclaurin series for the function e to the x, and then also the interval of convergence. So we have the closed form already from the previous video. Now we need to find the interval of convergence. So remember that Maclaurin series and also Taylor series are just specific types of power series, meaning that if you need to find the interval of convergence, you do it the same way as with a power series by using the ratio test. So we will use the ratio test to find the interval of convergence. Oop, I missed a word there. To find, that is important. So we are going to set up and simplify our ratio. The ratio of, the magnitude of the ratio of a sub n plus 1 over a sub n. Here that means we are going to have x to the n plus 1 over n plus 1 factorial. That will be all over x to the n over n factorial. We're going to have a magnitude there. We've seen similar simplifications to this before, so I'm going to go through this pretty quickly. The x to the n, oops, not that way, will cancel out with most of the x to the n plus 1, so we'll just be left with an x to the first power. And that is a magnitude because x could be positive or negative. So we'll have an x in absolute values, and then we know that our n plus 1 factorial and our n factorial will simplify so that we will just have an n plus 1 in the denominator. Now we need to evaluate our limit as n goes to infinity of the absolute value of x over n plus 1. We know we can pull that x out of the limit. So the limit as n goes to infinity of 1 over n plus 1 is just equal to 0. We have magnitude of x times 0, which is just 0. And by the ratio test, that will always converge, which means that our interval of convergence is all x values, so x between negative infinity and infinity. And that completes example 1 for us.